Unit 9, Molecular Geometry, pages 220 to 228, Molecular Polarity. Polar and nonpolar molecules, not to be confused with polar and nonpolar bonds. In Chapter 7, we discussed the concept of polar bonds, meaning if you looked at the differences in electronegativities, then you can compare them to the little chart we had, and if you had above 0.4 but below 2.0, then you had a polar covalent bond between these two atoms. This would be nonpolar covalent, this is polar covalent, and this is nonpolar covalent. Electronegativity measures the pull on electrons in a bond. When the difference in electronegativity is large, electrons are pulled closer to the more electronegative atom, giving the atom a partial negative charge. In general, when the atoms in the bond are different, the electronegativity is usually different and the bond is polar. More precisely, if the difference in electronegativity is greater than 0.4, we say the bond is polar. See the table on page 170. So recall the HF molecule here, where we looked at the differences in their bond electronegativities, and it's polar. However, the electrons are pulled more towards fluorine because it has a higher electronegativity value, which gives it a partial negative charge, giving hydrogen a partial positive charge, and creating what's called a dipole, which means the electrons are being pulled in this direction. So let's talk about polar molecules as a whole. The bonds in CO2 are polar because the electronegativity of oxygen is higher than carbon. However, since the two dipoles are oriented in opposite directions, the dipoles cancel, and we call this molecule nonpolar. So here we have a polarity, or a dipole, pulling towards the oxygen and from the carbon, and the same thing in the other direction. However, because these are equal and opposite of one another, they do what's called cancel, and when dipoles cancel, you have a nonpolar molecule. The bonds are polar, but the molecule is nonpolar. So if you think of this analogy, if the dogs have equal strength and pull in opposite directions, their efforts cancel. But if you have a big, strong dog on one side and a little wimpy dog on the other side, the big dog is going to win. There's going to be an overall pull in one of the directions. The molecule OCS is polar because the dipoles do not cancel. The dipole oriented towards oxygen is much larger than the one oriented towards sulfur because the electronegativity of oxygen is much higher than that of the sulfur. So there's actually an overall dipole going in this direction because this is stronger than this one is. To determine if a molecule is polar, you must first know the molecular geometry. So when do dipoles cancel? Dipoles cancel when all the domains are the same, and the electron domain geometry is one of these basic types. And remember, when dipoles cancel, we have a nonpolar molecule. So if you have a linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, or octahedral molecular geometry, then you're going to have a nonpolar molecule. The next two pages show all of the cases that give rise to polar and nonpolar molecules. For the more complex geometries, it's not always easy to see how the dipoles cancel. In high school physics, you learn about vectors. When the dipoles in a trigonal plane geometry are written as vector components, it's easy to see why they cancel when all three domains are the same. The diagram for BH3, which has a trigonal planar geometry, is seen below, and the way that the vector components are written, they are in such a way that all of the dipoles cancel with each other. For water, the dipoles do not cancel, and this results in a net dipole. Water has a tetrahedral electron domain geometry. The dipoles cancel when all four domains are the same. For water, two of the domains are non-bonding, or lone pairs, here and here. And so because there are these two lone pairs present, it causes you to have a bent configuration, which means your dipoles are actually going to work their way up and cross and not cancel each other. So we actually have an overall net dipole going in the upwards direction. You're going to need to memorize when you have a polar versus nonpolar molecule. So when we have two domains, a linear configuration, it's nonpolar as long as these are identical. But if they are not identical, then it becomes polar because there is a pull more in one direction than there is in the other. When you have three domains, as long as they're all identical, then this is going to be nonpolar. But if one of the three domains is different than the others, then it's going to become a polar configuration. When you have four domains, 4 identical domains is going to equal nonpolar, but if one of the 4 domains is not identical to the other 3, then you're going to have a polar configuration. 5 identical domains is going to be nonpolar, and whenever you have the linear configuration for 5 domains, then that's going to also be considered nonpolar. So this is an exception because all 5 domains are not identical, but if you end up with the linear 5-domain molecule, then that's going to be nonpolar. It's polar whenever it is seesaw, has 1 lone pair, or if you have a T-shape, then that should also be considered polar. When you have 6 domains, 6 identical domains is nonpolar. It's also nonpolar when you end up with square planar, because all 4 of these are in a flat square and in the plane. If you're ignoring these 2 guys, you can make a flat square with that, and so they're going to cancel with each other. So that's going to be nonpolar. If you end up with 2 lone pairs on the center atom, or just 1 lone pair on the center atom, then these are going to be considered polar. So you really only need to know that if everything's identical, it's nonpolar, or if it's linear or square planar, then it's nonpolar. Example 9.53, determine which of these is polar and which is nonpolar. So let's draw the Lewis structures first. First, let's look at pH 3. We have a total of 4 domains. 3 of them are identical, but the 4th one is not. So this molecule is going to be polar. Here we have 3 domains. They're all identical, so this is going to be nonpolar. Here we have 4 domains. They are all identical, and so this one will also be nonpolar. Here we have a total of 5 domains. So we want to call it polar, but remember there's an exception if with 5 domains we have a linear molecular geometry. This one actually has a seesaw geometry, and so it is not one of our exceptions, and so it is going to be polar. Here's your note card for this section. You have a nonpolar molecule when all domains are identical. There are 2 exceptions. When you have a molecular geometry that's linear when it's 5 domains, or if you have a square planar when you have 6 domains, these are going to be considered nonpolar. They have lone pairs on them, but the configuration has dipoles that cancels. If it's polar, then it's going to have domains that are different or not identical.